to use machine learning to build predictive models over historical data, a data scientist must identify training examples and select valid data prior to each example. We call this vital part of the data science endeavor prediction engineering. To start, a data scientist first defines and implements an outcome to predict. For example, will a customer make a purchase in the electronics department next month? With the precise definition of an outcome, the data scientist must implement a way to identify where the outcome occurred in their dataset. This implementation requires an approach to scan over the entire dataset looking for the outcome or label. The result of this is a 3-tuple of customer ID, timestamp, and label. Oftentimes, the outcome of interest will have happened multiple times in a customer's lifetime. To reduce the bias of learning from a single customer, the data scientist may attempt to limit the number of training examples per customer, resulting in appending additional code to their implementation. Even once the proper number of training examples per customer are selected, more code may still be needed to enforce other constraints, such as separating consecutive occurrences by at least 1 month. As the list of refinements to the prediction problem grows, the implementation becomes increasingly tied to the specific details of the problem at hand. This results in solutions that are difficult to reuse with new prediction problems on the same dataset or when new datasets are encountered. To address the growing need for predictive models, we must give structure to this process. Our efforts to do this resulted in the Label, Segment, Featurize framework. LSF structures predictive modeling with proper abstractions and is designed such that the same framework can be used for problems from disparate domains like retail analytics, predictive health maintenance, and transactional fraud. In LSF, the user writes a labeling function that is used to calculate labels for the dataset. The labeling function is provided a snapshot of the data and a cutoff time, known as STC. Provided these inputs, the function returns the label that should be predicted using only data from before the cutoff time. In the label step, all the events for a single training example are assembled and ordered by time. Then, the labeling function is intelligently used to scan this series of events using our traversal algorithm. This algorithm takes parameters for where to start the search and the granularity in which to scan. The scan produces labeled points in time that can be used for prediction. In the segment step, we can filter out some of these points in time according to the constraints of the particular problem, as well as further specify the data that should be used for learning. The output of segmentation is a list of learning segments that specify the first and last times of data that can be used for prediction. The Featurize step converts the learning segments to feature vectors that are ready for machine learning. Because the learning segments specify a segment of data that is allowed to be used, the feature computations can be automatically augmented to strictly include historical data from before our label. This prevents common predictive modeling pitfalls such as leaking label data into our feature vectors. Using the Label, Segment, Featurize framework, a data scientist can easily configure a prediction problem and reuse common pieces of the prediction engineering pipeline. This enables organizations to scale up their data science resources to address the growing need for predictive models.